First, the reactants of the equation include 2 H2 molecules and 1 O2 molecule. All the atoms are diatomic because 2 atoms are joined together. The H atoms are joined by a single nonpolar covalent bond, since the electronegativity values include 2.1 minus 2.1 equaling 0.0. The O atoms are joined by a double nonpolar covalent bond, since the electronegativity values include 3.5 minus 3.5 equaling 0.0. The atoms are stable since the octet rule is satisfied, and there is no potential energy. To break the H bonds, 436 kilojoules per mole of energy is needed for each bond. Since there are 2 bonds, 872 kilojoules per mole of energy is needed. To break the double bond joining the O atoms, 498 kilojoules per mole is needed. So, 436 kilojoules per mole plus 436 kilojoules per mole plus 498 kilojoules per mole equals 1,370 kilojoules per mole in potential energy. The energy is provided by a spark, or, in our experiment, a match. All the H and O bonds are now broken. At this point, the atoms have the most potential energy. 1,370 kilojoules per mole of energy is present in the free state. Atoms are the least stable and the octet rule is not satisfied. Energy is now produced. When the OH bond is formed, negative 463 kilojoules per mole of energy is released. There are 4 OH bonds. So, a total of 1,852 kilojoules per mole is released. Because there was 1,370 kilojoules per mole potential energy, and 1,852 kilojoules per mole was released, negative 482 kilojoules per mole remains, making the reaction exothermic. The energy is released through heat, sound, and flame. H2O, or water, is now formed and satisfies the octet rule. The compound is very stable and has low potential energy. Other products include fire, heat, and sound.